Right. Good morning. Today is March March 13, 2025. This is General Chemistry 1, Section 72, Spring 2024-2025 semester, and the time is 10:20 a.m. Now uh, we still in chapter number 6, yes? And we finished last time, we finished the slide number 3. And we are talking about the thermochemistry. That's about the chapter. And I'm going to continue as from the slide number 4. Slide number 4. Now, in this slide here, I explain what is the thermochemistry before. That means it's a chemical reaction that it is associated or linked with actually energy absorbed or energy released in there. Now, that's the thermochemistry. So thermochemistry is the study of the heat change in a chemical reaction. Now, when we talk about a system, that means a system that we're going to study. Always we have to study a certain system. If you have a system to study, so the system is the specific part of the universe, that means of everything that is of interest in the study. Yani, if I have, for example, a solution and I want to study what's inside, this will be my system. Right. When we talk about systems in here, we have three types of system. One system, it is called an open system. It is open system. Open, it means open to the atmosphere. Look at this container. So you have the flask in here containing a solution. It is open to the atmosphere. That means some of the solution might leave or some material can come in. That means something can come in, something can be out. It's not closed. So we say it's open. Also, the heat can go out and the heat can go in because it's not an insulator. Is it okay? So that's why we say we call it an open system. Okay. The other type of system, we call it a closed system. Closed system. Open or opened, closed or closed. Now you can see in here the system is closed. As the system is closed, that means the material cannot leave the container and no material can enter the container. Is it clear? But the heat can go out or the heat can go in because it's not insulated or isolated. Now, the last type of the system, we say it is an insulated system. Insulated system, or sometimes we call it isolated system. Isolated system. In this isolated system, it means the system, first of all, it is closed. No material can leave, no material can get in. Okay, that means the mass cannot escape, no mass will go inside. At the same time, because it has a jacket like a thermos, you know the thermos when you go to picnic, you've got some thermos, you put coffee in there, and the hot coffee remains hot for a long time. Why? Because there is a jacket in here, we call it like a jacket, okay, that will prevent the heat to escape and also will prevent the heat to come in, and we call it insulated system. Is it clear? So these are the three types of system we can come across. Let me carry on in here. Now, when we have a system or thermochemical equation, the thermochemical equation can be exothermic reaction or endothermic reaction. When we talk about the exothermic reaction or exothermic process, is any process that will give off the heat, gives off heat or transfer the thermal energy from the system to the surrounding. Yani, if I have a certain material in here, I have a chemical reaction. I have A plus B in here. Now, this is my system. So anything around my system, we call it the surrounding. This is called surrounding. Okay? Anything around the surrounding and around the system, we will call it from now on universe, العالم. universe. Okay, is it clear? So you have the system and the surrounding. Now, if I have a beaker, or if that's my mobile, that's my system I want to study. Anything I want to study is my system. But if this mobile is going to give up heat, all right, where the heat will go? It will go to the atmosphere. That means to the surrounding, whatever is surrounding. And this mobile and the surrounding and everything around us is going to be called the universe. Okay? Now, exothermic reaction. Now, in exothermic reaction, suppose I'm having H2 plus O2 will give me H2O. Chemical reaction to produce water from the oxygen gas and the hydrogen gas. Now, you can see in here some energy is coming out. Okay, if the energy is coming out, remember one thing: on the left-hand side we have reactants, and on the right-hand side we will have the product. And this is actually how we write a chemical equation. If the energy is a product, it means the energy is being released. That means we call it exothermic reaction. If the energy is a reactant in here, as you can see in there, that means the energy is needed for this reaction to take place. That means the energy in here as a reactant, the whole equation, we call it endothermic reaction. Endothermic reaction or endothermic process, because this reaction will never take place unless you give it some heat. It will take some heat and then the reaction will take place to give me the product in there. That's another example of actually this is another example of exothermic reaction. Yani, if I'm having water gas, yani water vapor, if I want to make it change it to water liquid, what I have to do? Condensation. صح? Condensation means what? It means now because the water molecules are flying up, that means they have a lot of energy, yes? If I take the energy from the water, what will happen to the water? It's going to become as liquid. It's going to fall down, as simple as this. All right. Now, which means in here, for this water gas to go into liquid, it has to lose some energy. That means it's going to emit some energy. But if I want the liquid to go into gas, the water liquid to go into gas, what I need in this case? I need to give it some energy. I need to heat it. It's better, yeah? Okay. Right. Now, again, endothermic reaction in here is a process in which the heat has to be supplied to the system from where? Who's going to give the heat? The surroundings, huh? Okay, from the surrounding. Now, these are two examples in here where you have endothermic reaction, where the heat or the energy is actually, it is coming from the surrounding, which means it is actually a reactant. Now, let's have a look at this plot in here, just to have an idea. Look in there. The energy, if you look at the scale in here, the energy is going up. Low energy, high energy in there. You can see the arrow in here. So that's how the energy is going up. Now, when we have H2 and O2, hydrogen has got a huge amount of energy, potential energy, yeah? Oxygen has got a huge amount of energy, okay? When you put them together in here, what will happen? A reaction will take place. As reaction will take place, they will get converted to water. The water doesn't have huge amount of energy, yes? Otherwise, we can use the water in our car to run our car, yeah? So it doesn't have. That means this will have a low energy in here. These two have a very high amount of energy, potential energy. When these are converted to water, what will happen? The difference in energy, so that's the energy E1, and that's the energy E2. Higher energy, lower energy. Where the difference will go? The difference will get released. They will go actually to the surrounding. As simple as this. All right. If I take another example here, again, high energy, low energy. Now look at the mercury. I'm sorry, HGO. Okay, mercury 2 oxide. Okay, or mercuric oxide. Now, this mercuric oxide has got a very low energy. So this has energy E1, which is low energy E1. Now, in order to break it down, okay, Okay, if I want to break this compound into pieces, what I have to put? I have to put some energy. Now, if I add some energy in here, I need energy in order to break it down. Once I put some energy, this will be breaking down of the compound, and this will split into Hg and O2. And Hg has got high energy, and O2 have got high energy, so the energy in here is high. Now, the difference in energy between this and this is coming from where? From the surrounding. So the surrounding give this energy, and this HgO will be converted to Hg and O, and we call it endothermic reaction. So this reaction is endothermic, and this reaction, I would say in here, minus energy, which is the delta. This is plus energy, and this is minus energy. The system lost energy, and the system in there gained energy. Is this clear? Yes. Okay. Okay. Let's go through the next slide here. Okay, thermodynamics. يعني thermodynamics. When we say thermodynamics, dynamics means what? Motion, exactly, motion. Dynamics means motion. Thermodynamics, that means the motion or the movement of what? Of the heat. Can the heat move? No, but it creates energy. The heat can move. Now, the heat, if I have a hot object and a cold object far away from each other, the heat will not jump from one to the other. Only way, if they are actually close to each other, touching each other, now the heat will go from higher temperature to the lower temperature. So that means the heat is moving from place to place. When the heat is moving from place to place, we say it is what? Thermodynamic. Heat is the thermodynamic. Now again, take a hot object in here and put next to it a cold object in there. So what will happen? The heat is going to go where? The heat in here will go from here to there. Am I right? From the hot object to the cold object. Does it go from the cold object to the hot object? No. Yes, it will go as one. That's exactly when I'm having a lot of students in this class. Few student outside, the door is closed, no student can go out. No student can come inside, so yeah. But the moment I open the door, many students, because large number in here, many students will go out, but this will not prevent some of the students from outside to get in as well. صح ولا لا? Yeah, that means some will go out, some will come in, but those who coming out is a lot. Those who coming in is actually less, and that's why you can see in here long arrow and actually or long arrow and short arrow. But with the time, what will happen? With the time, this one is going to decrease, this one will increase, and eventually the forward and the reverse heat will be equal to each other, and then we can say we reach a thermal equilibrium. Thermal equilibrium. Is it okay? Now, which means now this heat at the end, when after a certain time, the heat will go always in here. The heat will go always in there at the same rate. Now, in here, let's say that was 60 degrees Celsius, and this one was 40 degrees Celsius, yes? 60 and 40. At the end, each one is going to be 50 degrees Celsius. You understand what I'm saying? And this one is 50 degrees Celsius, but always the heat will go in and out. It will never stop, all right? But at the same rate, because it is at the same rate, the temperature on both sides remains the same. Is it clear? Good. Now let's talk about the thermodynamics so you know a little bit about it here. Thermodynamics is the scientific study of the interconversion of heat and other kind of energy. But there is one important thing that you have to memorize and understand perfectly well, which is called the state functions. Very important thing in here. State functions are the properties. I will read it, but I will explain it in a better way. State functions are the properties that are determined by the state of the system. State function. state of the system, regardless of how that condition was achieved. And that's very important, regardless that how this being achieved. And here we talk about energy, pressure, volume, and temperature. All right? Now, let me explain it in a different way. I need to erase all of this. I need a space, just a space. Now, there is a picture right in there. If you can look at it, it shows a mountain, and you have actually the summit of the mountain, al-Qumma, the summit of the mountain, and you have yellow line and the green line in there, which means practically what we've got in there. We've got one person standing in here, another person standing in here, and both they are climbers. They want to go up to the summit. One will follow a path which is in yellow, and the other one is follow actually again in green color. Another one is going to follow it as a red color, and so on. There are some climbers, all of them, they want to go to the top. Yani, actually, if I'm having a summit in here and one person standing in there, and this one, maybe he will go straight up. Yeah, you understand what I'm doing? Okay. Now, another person standing at the same area in here, but this one, he will not go straight for some reason. He will go like this, like this, like this, and then eventually he will get to the top of the hill. You understand what I'm doing? Yes? Who will spend more energy? The green one okay. He should spend more energy. But when it comes to what we say state function, they're not going to spend more energy. No, both will spend the same amount of energy, and that's how we're going to understand it. Now, of course, if I'm going to buy a ticket from Dubai to LA, Los Angeles, maybe I pay $1,000. But that's a direct flight. If I want to buy in real life, if I want to buy an airline ticket to go from Dubai, not direct flight to the LA, but it goes to London, and from London to wherever, to wherever, to wherever, and get to there. Do I have to pay more money? I have to pay maybe more, maybe less, whatsoever. But it's not going to be the same amount in real life. But from now, to understand this, understand that whether you go direct flight from Dubai to LA, you pay 1,000 dirham. If you go through many places to reach LA from Dubai, you also pay 1,000 dirham. Is it okay with you? Yeah, okay. That's what we're going to understand it in here. Yeah. Yani, actually, what will happen? It means in this case, imagine that this guy will go up and then comes down. As he's going up, he's going to give some energy. As he's going down, he will get some energy. Giving energy, coming energy, plus, minus, plus, minus, plus, minus. And at the end in here, the energy spent by each one of them is going to be the same. All right? Is this clear? So that's how we're going to understand what it means, the state function. All right. So regardless how the condition, regardless what the way is going, so it's going to be the same. Now, look at the potential energy in here. We're referring to this photo. The potential energy of the hiker one, you have one hiker and you have another hiker, and hiker two is the same, even though they took different paths. You understand how it is? Yeah? Is it clear? Good. Now, we will go further. We will talk here about the delta U. U is the internal energy. Delta U, it means what? يعني delta V. Delta V is the volume change. صح? يعني last volume minus the initial volume. Okay? Delta T, temperature change, and so on. Now, delta U will be U final minus U initial, P final minus P initial, V final minus V initial, and always we take it as delta, delta, and delta, delta T, and so on. Let's move a little bit further to talk a little bit more about it. Let us go through the first law of the thermodynamics. Now, since there is a thermodynamic, that means the heat goes from one place to the other place, okay? That's the motion of the heat. It means there will be some laws that we have to follow. The first law of the thermodynamic, it says, energy can be converted from one form to another form, but cannot be created nor can be destroyed. Yani, if I'm having 100 kilojoule, I can change it to whatsoever, but the amount will be still 100. No more, no less. And that's called the law of the conservation of energy. Now, look in here. Delta U of the system. You have a system. And the delta U of the surrounding. Yani practically, if the system is going to release some energy, this energy released is all the energy released will be captured by who? By the surroundings. Huh? Yani the energy released must be equal to the energy absorbed by the surrounding. Energy released by the system must be equal to energy absorbed by the surroundings. Huh? Yani delta U, delta, no, of course, this one, delta U, that means it's negative. Huh? And that's what we, okay. Another thing, when we talk about exothermic reaction will give me the energy. And by default, the energy will be negatively charged. يعني negative. If I'm losing money, I say minus 5 dirhams. Yeah. If I'm gaining money, I would say plus 5 dirhams. Yani plus from now on means I gained. Minus means what? I lost. Okay. Now, if the system is exothermic, that means the system will give some heat, then the heat will go and the surrounding will actually gain the same amount of heat. Yani if the system is releasing 100 kilojoules, the surrounding will gain plus 100 kilojoule. So minus 100 plus 100 will be equal to 0 because the delta U is equal to, of the system is equal to the surrounding as absolute value. Now, delta, or we can say delta U of the system must be equal to, it should be equal to delta U of the surroundings. Yani 100 kilojoule, the other one 100. But to make a difference between them, one is gaining and the other one is losing. Now we have to use a sign minus because they are not exactly equal in sign. They are opposite sign, but they are equal values. Is it clear? Okay. Now, look in here, for example, C3H8, that's the propane. Propane is a gas, when you burn it, you will obtain CO2 and you will obtain H2O, plus, of course, you're going to obtain some heat in here. Heat or energy. You will get some heat, you can get some energy in there. Now, since the energy is being released, so what we call this reaction, we will call it exothermic reaction. So that's an exothermic chemical reaction. Now, chemical energy, now again, you burn something, you get a flame, and you get a huge amount of heat. The heat will be produced by burning the propane, but absorbed by the surrounding. It means I can put a pot of water in there and heat my water. All right. Chemical energy lost by the combustion, of course, the chemical energy is lost by the combustion, is the same chemical chemical energy that is gained by the surrounding. Nothing is lost. Nothing is gained or created. Now, another form of the first law of delta U of the system, energy of the system, internal energy of the system, if you want to put it this way. Now we have two types of heat in there. You have Q, which will be called the heat. We call it the heat. That's a Q, or you can write it as small q. Okay, small q if you want. And you have W, and the W is the work. W is the work, all right? Now, the heat in there, now, so far we know that the heat can be what? The heat, it can be either negative or it can be positive. صح ولا؟ Now, if it is negative, that means it is an exothermic reaction. If it is positive, it is endothermic reaction. Is this, yeah? What about the work? The work also, if you look at the work itself, the work can be either positive or the work can be negative. Yani the work, these are energy, the work. Okay. The work can be positive or the work can be negative. Now, if I go back to the Q is positive. That means it's absorbing heat. The system is absorbing heat. Q is negative. That means the system is actually releasing the heat or energy. Now, work is completely different in here. That means it's to do with the energy. It is associated with the energy, but the energy could be positive or could be negative. Now, work, if I'm doing some work, what does it mean? Am I losing energy or I'm gaining energy? I'm losing. So if I'm doing work, that means the work is minus. ما في exo. ما في. It's minus, negative. The work is negative if I am doing the work. Now, let's say I am on the ground floor and I want to go to the first floor here. I have to go through the stairs, yeah? That means I'm spending some energy. So the energy is what now? The work is what? Negative or positive? Negative. Now, let's take another case. I am at the ground floor and I want to go on the first floor, okay? But in here, somebody will carry me up. He will hold me and he carries me through the stairs to here. Am I losing energy? I am gaining energy. Yani the first case, the work was done by the system. I did the work, I walked up. In the second case, the work is being done on the system. Somebody took me and lift me up, all right? Right, so this is actually done on the system. Now, again in here, so the work can be positive or negative, and the heat or can be positive and negative. Delta U in here is the change in the internal energy. So remember, U is the internal energy. U is the internal energy. Delta U is the internal energy change or change in the internal energy. Q is the heat exchange between the system and the surrounding. W is the work done on the system or work done by the system. Now, if I look at the work, should work, what is the work? Work, if I'm walking in here, it means how much work I did, how long is the distance that I have walked. Yeah? Long distance, more work. Less distance, less work. So that's very important. But if you want to look at it in more details in here, I can have, you remember the gases, yes? I can have a cylinder in here, and I can have a piston in there, okay? And of course, I have a gas inside. You have gas, piston, and there. Now, if this is actually the volume V1 in there. Now, if something happened that I put some heat, for example. If I put some heat, okay, so I'm going to increase the temperature. If I increase the temperature, what will happen to the gas? The gas is going to push this, and the piston will go up to another level, yeah? So this will be another one, which is V2, okay? Now, how much is the distance between these two? It went from V1 to V2. That means practically it went through a distance of delta V. صح ولا لا? Yeah. And in here, what makes this one pushing is actually a pressure. There is a pressure. There is a force that actually moves the piston up. Now, how much the work? Now, this did a work. If this one was moved even higher, the work would have been much higher. Okay, if you put more pressure, the work will be more, and so on. So the work is related to the pressure that pushed the piston up and the distance by which the piston has been moved up. Or it can be moved down as well, because if I put a weight from outside, pressure from the outside, this will be pushed down, okay? So if it's going to push down, that means we're talking about compression, all right? If it's going to go up, we talk about what in here? The opposite of compression is what? Okay. Not stretching, it is expansion. Okay, this expansion, all right? Now, if I want to look at the work in here, the formula of the work will be equal to P, what's the pressure in atmosphere, multiplied by delta V. Delta V is a change in the volumes. But in here, we have to put minus in here. Why it is minus? Why? Because the work is done by the system, huh? It should be negative. Practically, it cannot be negative because the pressure is always positive. Delta V is always positive. But to tell you that this is actually the work has been done by the system, that means the system has has done the work, lost the energy, then I have to use, I introduce in here the minus in there. Okay? Now, again, if you look at it in different way, now if the V is going from V2 to V1, what will be delta V? V1 minus V2, which is negative, yeah? But negative times this negative in here becomes plus. That means the work is being done on the system. Somebody pushed the piston down. Okay? We move, okay. Now, again, in here, what you can see, sign conventions for the work and mustalah, yani convention. Sign conventions for the work and the heat. Now, the work done by the system is always negative. The work done on the system, it is positive. Endothermic reaction, that means the heat absorbed, it is positive. Q is positive, or Q is negative is if the system is exothermic reaction. Now, I think I explained already for you, okay? Why we write it as minus in here to make sure that the work is being actually negative, or it can be positive. I'm not going to go through a lot of things in here, but again, if you have a pressure multiplied by volume, this is the work, so what will be the volume in here? If I want to look at the volume is going to be, now if it's a cylinder, you know how to calculate the volume of a cylinder. Surface multiplied by the height of the cylinder, all right? So surface times height, so you have whatsoever, so I'm not going to go through the mathematics in here. And of course, the pressure itself is the F. The force is the pressure, and anything else in there, I don't think it's a good relation in here. Anyway, I think I skipped a lot in here, okay? I'm going to skip a lot. I'm going to go to something more important. A certain gas expands in volume from 2 liters to 6 liters at a constant temperature. Calculate the work done by the gas. Is it the work done by the gas or done on the gas? Of course, because the expansion. Perfect. Calculate the work if it expands against a vacuum. شو الفاكيوم؟ يعني pressure is equal to how much? Zero. الفاكيوم ما عنده pressure. Yeah. Or against, now you have to do the calculation under two conditions, or against a constant pressure, then you put a pressure and this has to extend. How much is going to, how much work is going to do in here? Now that's the pressure in here. Now, what we do, let's go straight in there. That's a strategy. We don't need this strategy. Again, strategy, from the strategy, we need to find delta V. Yeah, that means I have the initial volume and the final volume. Now, the difference in volume will be 6 minus 2, and that's actually 4. Okay, so, and the work, that's the equation for the work, minus P times delta V. In the first case, if it is in a vacuum, the pressure is equal to 0 in here, so 0 times V is going to be 0. That means it is 0. No work. There is a vacuum. You know, when you have a vacuum at home and you do it, what will happen? It will take things out. Yes, it will actually aspirate. Okay, and then that means there is no work. It didn't do any work. The machine did the work. Now, the external opposing is whatever pressure in here, 1.2. So you apply the same equation, but set the pressure as 1.2, and you will have it actually as much. That's minus. Minus, that means the work has been done by the gas, by the system. Okay. Now, to convert the answer, now the answer in here, the answer was liter times atmosphere. Of course, because this is actually in liters, this is in liters, and this is in atmosphere. But when we talk about the energy, we don't express it as usually as liter atmosphere. We express it as joule, as calories, and things like that. Now, if you want to convert it, let's say, to joules, now, I will never convert to joule unless you will tell me what's the relation between the joule and the liter times atmosphere. If you don't give me the relation, I'm not going to solve it for you, because I'm not supposed to memorize things all the time. Okay, you want to ask something quickly, please.
The minus, sorry, the work done by the system or on the system. Which one in another ضيع? Which one is gain and which one is lost?
Minus means losing, yeah. ما في losing.
Buy will on.
You talk about work or you talk about what?
Work done by the system or work done on the
I
system.
explained as example, work done by the system, that means the system did some work, it means it lost energy, yeah?
No. Okay.
Okay. Right. The work done when a gas is compressed in a cylinder, like shown in the whatever figure, during this process, there is a heat transfer of whatsoever. So that's a heat transfer. Calculate the energy. I don't know what example is this in here. Figure 5. The work done when a gas compressed, when a gas is compressed in a cylinder, like shown in whatever figure, is that much. So that's the work. During this process, there is a heat. Perfect. Now they're giving me W and they're giving me Q. صح? Now, during this process, there is a heat transfer from the gas to the surrounding. What does it mean? This is positive or negative? Negative. All right. Now, and in here, it is positive or negative? Okay, because it's compressed. Yani compressed. If there is a gas and you compress it, that means you put some work on it. Yes, that means the work is what done on the system. It is positive. So you have to understand to differentiate between plus and minus for the exo, for the Q, and for the W. You have to know exactly how it is. Okay, yani they sign and go. And because I don't want to trap you long. لا مش انت I'm talking about him. انتوا غير شيء. الصبايا don't have problem, but I have problem with the boys. Okay, you know, you can see some examples here. Okay, now calculate the energy change. How much it will be the energy change? So the heat will be equal to how much? Heat will be equal to W plus Q. صح? Now the W, how much is W? So this will be equal plus 462 minus 128. Make the calculation and you get whatever. That's the energy. That's it. Then energy includes the heat and the work. Okay? Right. Now that's the strategy in here, and that's what we have done. صح? And this one, and this one, and that's what we get. That's the delta U, that's the internal energy in there. Okay, now, enthalpy of and the first law of the thermodynamic, and now that's what we said. And you have to memorize this one, that the internal energy change of any system, it depends on the work and on the heat, on the work and on the heat. At constant pressure. Now, Q equal to, the Q is equal to delta H, and the work always equal to this much. You remember these equations, yes? That's from a chemical reaction, and this is depending on the pressure and the delta V in there. And delta U will be equal to delta H minus P delta V, or instead of saying delta H in here, you can say delta U, and they are the same. When we say delta H, from now on, you have to understand that there is a new parameter here, which is H, and the H, we will call it from now on the enthalpy. Enthalpy. When we talk about delta H, that means this is enthalpy change, yeah? Enthalpy change. Enthalpy change is the delta H, and we're going to use this one a lot in our reactions, okay? We always use delta H. Okay, enthalpy. Now we're going through the enthalpy. Enthalpy H is used to quantify the heat flow into and out the system in a process that occurs at constant pressure. What does it mean, constant pressure? Constant pressure, I have a beaker, I have A and B, I add them together, reaction will take place, but the beaker is open to the atmosphere. Open to the atmosphere, that means the pressure of the system is equal to the pressure outside. If I close it, that means I'm far away from the uh, from the system, all right, from the constant pressure. Now, occurs at constant pressure. Now the pressure must be constant. Now, look in here, delta H. If I'm having some reactants, because here we talk about a chemical reaction. You have reactants, and these reactants will give me the product. Yes? Will give me product. The reactants in here, they will have a certain enthalpy H. Okay, let's say of the reactants. The product will have enthalpy of the product P. All right. Now, how much energy? What will be the delta H in here? It will be equal to the enthalpy of the product minus the enthalpy of the reactant. Why is that? Because the end product always delta T is T final minus T initial. But when we say delta H, yani H final, who is the H final? That's the product, صح? Minus the H initial, who is the initial? Are the reactants, all right? Now, so delta H always equal to the enthalpy of all the products, add them together, minus the enthalpy of all the reactants after you add them together. As simple as this, right? Now let's have a look in here. Going back to the same thing. You have a piece of ice in here, okay? This is a piece of ice in there, water solid, okay? The piece of ice in here, look at the energy going up. If I'm going to change it into liquid, solid to liquid, that means I have to give it some energy. The energy I will give it, that means it is an endothermic reaction. Now, this has actually an energy E1, which is low, صح? And this one will have an energy E2, which is high. مظبوط? Okay. If I take the difference in energy in here, what does it mean? E2 minus E1. Yani, this is E1. Okay, it was that much. You give it some energy, you bring it to E2. How much the energy you give it is E2 minus E1. Okay, so delta E is actually the energy that has been absorbed or actually released. So the delta E in here is the energy that has been absorbed by the piece of the ice in order to melt to go into water liquid. Okay, now the other thing in here, so again, look in there, the delta H in this case is going to be positive or negative? طبعا لأنه the H of the product is much higher than that of the reactant. In here, that's the opposite. You have actually, for example, methane, and you burn it in water. You burn it in the presence of oxygen. Methane is actually a gas that has a huge amount of energy. That's why we burn it to get heat out of it. That means the amount of energy in here is very high, صح? But this is, when I'm going to burn it, the reaction will go there. These are going to be the products, huh? These are the product, and these are the reactants. These are the reactants. And the products, you end up with CO2 and H2O. Does the CO2 has a lot of energy inside it, internal energy? Water has got, you're right. If it was, we would have actually used CO2 to get energy out of it, but it has a very low amount of energy. Now, if I take the difference between the final, that's the final, remember? And this one is the initial. Final minus initial will be what? Negative, طبعا. Negative means what? It's actually releasing heat. When I burn the methane, I can get huge amount of heat. Now I can make my cooking. I can actually warm myself up and so on. Now, in the first case, the enthalpy of the product is higher than the enthalpy of all reactants, and therefore delta H is positive, and this reaction is endothermic. Huh? In here, it's the opposite, all right? So I'm not going to go again through it, but clearly delta H is negative. When the delta H is negative, it means the reaction is exothermic reaction. Excellent, good. Now, Is delta H in here negative or positive? Thermochemical equation. Is this delta H negative or positive? I will not ask you a question like this in the quiz, right? معقول اعطيكم اياها positive واسكو positive مع negative. Why not? Okay, why not? Now, heat absorbed by the system from the surrounding delta H is positive. Of course, delta H is positive. خلاص عرفتوها هلا. No need to give it to you. Right. Now, let's go through this, probably this an example. 6.01 kilojoules are absorbed by every 1 mole of ice. يعني if I have شو يعني 1 mole of ice, how many grams of ice?
شو الايس؟ ايس ووتر صح؟ يعني 18
خلاص, that's it, 18. Every 1 mole of water is 18 grams, yeah? يعني 1 mole of ice is 18 grams. يعني if I want to melt 18 grams, I need to give it 6.01 kilojoule, okay? And this will be absorbed ice that in order to melt at 0 degrees Celsius. طبعا, if I have an ice, the temperature can be 0 and below because it's solid. If it is at 0, still it is solid. Now I have to give it little amount of energy. Once I give it some energy, now it's going to change to what? To liquid. What will be the temperature of the liquid? 0. The same. Because the melting point is the temperature. شوفوا, melting point is the temperature at which the solid starts going to liquid. Freezing point is the temperature at which a liquid will start going into solid. Yani when I have a piece of ice, if I give it some heat, still it is 0. Now when I start seeing really some of the ice being going into water, whenever I see it, now I know that this my the melting point, and this melting point will be 0 in this case. Yes. All right. And if I keep on going, melting and melting, the temperature is still 0, 0, 0, 0 until all the piece of ice is going to melt completely. If I keep on giving heat, now the temperature will go up and higher. Yeah. Okay. Until we'll go to 100 degrees Celsius. At 100 degrees Celsius, it is still liquid. But if I give it a little amount, when I start noticing there is a vapor coming out, so this will be the boiling point. And the boiling point, as a definition, is the temperature at which the liquid will start going into vapor. Is it okay? Right. Now, again in here, look in here, the water solid and water solid, change it to water liquid. It means I have to put some heat in here, and this amount of heat is equal to 6.01 kilojoule for every 1 mole of the ice. Okay, so that's the enthalpy change. We move a little bit further. Is the delta H positive and negative? In here is going to be شو? It is going to be negative طبعا, because you're burning, and that's what we said before. Let's have a look at this example. 890 point whatsoever kilojoules are released. I think the time is almost up. 10 minutes. 890.4 kilojoules are released for every 1 mole of methane. So you have the methane, we're burning the methane, and that is combusted at 25 degrees Celsius at 1 atmosphere. That's according to this equation. Now, instead of saying anything in here, everything in there, I don't have to say it. I can write it immediately right in here. Finished. That's it. Okay? So delta H is equal to minus whatsoever kilojoule for every 1 mole. If I have more moles, the energy will be more released. Less moles, less energy. More gas, more energy. Less gas, less energy. Okay? Okay. Now, thermochemical equations, now, from now on, when we say thermochemical equation, it means what I have to do. I have to write the equation perfectly well, perfectly balanced, and this will give me C plus D, let's say, in here. And I leave a space, and I will write in there the delta H of the reaction. I will write RXN. delta H of the reaction, and this will be equal plus or minus, let's say that's minus 111 kilojoule, okay, or kilocalories, could be whatsoever. Now this is called thermochemical equation, like the one you can see in here, like the one you can see in there. Notice when you change the ice, okay, the water ice into liquid, you melt it. It's an endothermic reaction because you have to put energy. But if you want to change the liquid, I want to freeze the liquid, what I need in here, to freeze the liquid, then the delta H is going to be negative. That means I have to take the energy from the compound in order to get it closer to each other. Yeah. Okay. All right. Now, okay, thermochemical equation, and that's the main thing in this chapter in here, as we know about, and we want to play a lot with this thermochemical equation. You know what the word means? Manipulation. تلاعب. Manipulation. But now pay attention. I will make it easy for you. Everything here. Manipulation. If you have a pilot, fighter jet pilot, and he wants to go and fight with his airplane. Okay. Now he can do some manipulation, right? He cannot go straight into the target. He has to do manipulation, but his manipulation will depend on what are the possibilities of his manipulation. He cannot invent manipulation. Depends on the quality of the water of the airplane and so on. So in here we're going to do manipulation, but this manipulation for the reaction, for the thermochemical reaction, and we have three rules in there. And the first rule, keep it in mind right now. Rule number one, if I have a thermochemical equation, and if I reverse this the thermochemical equation, I must reverse the sign of the delta H, okay? So that's rule number one. Notice in here, what I did in here, I reversed this equation. So this equation was reversed. The equation was reversed. So because I reversed, it went from plus into minus, but the amount is the same. Is it clear? So that's rule number one of the thermodynamics. Rule number two, if I have a thermochemical equation, and if I multiply the equation or I divide this equation by any coefficient, I have to do the same thing with the delta H. Yeah? Yani if I take this one, for example, and if I multiply this one by 1 million or multiplied by 5, let's say, then this will be 5. This will be 5, and this will be multiplied by 5. Is this okay? If I divide it, I have to do the same. So now we've got two rules, okay? Reversing the equation, you have to reverse the sign of the delta H. Multiplying the equation or dividing the equation by a certain parameter or certain coefficient, you have to do the same in there. So now we have two things in here. Now, in here, if I take this one, that's the example, they multiplied by 2, then you have to multiply the delta H by 2. Now, again, if you multiply or if you divide, you have to do the same in there. Rule number 3, which they didn't say it in here. Rule number 3. If I have, for example, H2O, for example, solid in here, or liquid, plus whatsoever, X, plus Y, and this is going to give me H2O, for example, gas, plus Z, plus W, I added two maybe equations together. Now, I am not allowed to cancel H2O and H2O from both sides of the equation. The only way that I can cancel any compound from both sides of the equation, only if they have the same physical state. If they don't have the same physical state, I cannot cancel them. For example, here, if I go gas and gas, now I can cancel this in there. Otherwise, I am not allowed. So now you know the three rules. Is it okay? We don't need more than these three rules. The physical state of all reactants and products must be specified in the thermochemical equation and here you have to say water solid, water liquid, liquid and gas and so on. Notice one thing in here. When I'm going to melt the solid into liquid, I need to give it certain amount of energy, yes? 6 kilojoule. But if I want to get the liquid into gas, I need how much? More. Is this possible? Of course, because melting, it's easy. You give it some more energy, it will melt. But if I have the water in here on this table, and I want it to go into vapor, what I need? I need a huge amount of energy because there is always a pressure on it. I have to overcome the pressure. That means I have to make sure that this water molecule can go up and up against the pressure and then can fly in the sky. All right, and that's why much more energy is required for this case. Okay, so as a common sense. Okay, given the thermochemical equation whatsoever, so you have this thermochemical equation. Is it endothermic or exothermic? It is exothermic. Do you think this reaction is okay, or there is something wrong in it?
Unbalanced.
It's not per mole, because how many moles you have in here? 2 moles, huh? If it was 1, we can write it per 1 mole. But since reacting of 2 moles of this, it's not per mole anymore, huh? So that's wrong from your textbook, okay? Or from the slide, whatever. Now you have given the thermochemical equation. Calculate the heat evolved when whatever grams of SO2, and they give me the molar mass of SO2 is converted to SO3. What we do in here? Do we work with grams? So I divide this one by the molar mass, huh? Divide by molar mass. Now I get the number of moles of SO2, number of moles of SO2. So now I'm working between what? Between SO2 and this one. I know that every 2 moles of SO2 by reaction is going to give me minus 198.2 kilojoules. So the number of moles of SO2, which I have just calculated, will give me how much? X. Cross multiplication, and X will be equal to the number of moles of SO2 multiplied by 198.2. طبعا it is negative in here. 0.2 ما هيك? Okay, divide by 2, and that's what we get. Very simple, all right? Okay, now let's have a look in here. We know that every 2 moles will give me this one. You see the difference? For every 2 moles, it gives in there. We don't say per mole. And that's the contradiction. In there, what they said? They said minus 198.2 per mole. لا مش per mole. It is per 2 moles. صح ولا؟ And that's why I took out per mole, because it's not per 1 mole when you convert 2 moles, actually. Now, again, that's a strategy. It's a strategy. Now, what we did, we actually got the grams, divide by molar mass, and we got the number of moles. Multiplied by minus whatsoever, divide by 2, and we got actually the delta H in here. Delta H will be in kilojoule. طبعا is going to be in kilojoules. Okay, less than 1 minute we have. Okay, I think we can leave this one for next time. Okay. 27, yes. Thank you for your attendance, and see you next week, inshallah. أهلا أهلا.